Okay, we're going to talk about probably what I wish would have been a little bit earlier in this chapter, and that is about graphing and transforming quadratic functions. So this is transformations of quadratic functions, and we're going to start with a little reminder about lines. So what form is this line in? It's actually in none of the forms that the book described. If you remember, they said that for a standard form, they wanted us to have a positive leading coefficient. So we can multiply everything by -1 here, and I'll get 3x minus y equals -1. But let's say that is standard form. Okay, what other forms were there? Well, there's slope intercept form, which is the mx plus b. And if you remember, we can get this guy to look like that by getting y by itself. And maybe the reason they wrote it this way so that would be easy to get y by itself, because I can just add 3x to both sides. And I get y equals 3x plus 1. So what do we have? We have standard, and we have slope intercept, and then you have the point slope. Y minus y1 is m, x minus x1. And they didn't give me a point necessarily to go through here, but slope intercept form does give me the slope is definitely 3. So let's just use the y-intercept, which is 0, 1 here. And we'll use this as our point. So y minus 1 equals 3, x minus 0. Okay, so this would be point slope. And if you remember, they're good for different things. Like, what is the purpose of this? Sometimes standard form is easy to write in. If it's a linear combination, it's good for finding the x and y intercepts. Quite a few of you found x and y intercepts that way when you were doing the linear inequalities. But everybody's favorite probably is this guy here, 3x plus 1, mx plus b, slope intercept form. Why do we like it so much? Because it's ready to graph. It tells us a lot just by looking at it. By looking at it, I know that the slope is 3 and the y-intercept is 1, and I don't know so much information without doing some math on this one. This guy tells me quite a bit of information too, but the problem with this formula is that people tend to forget it a little bit. The slope is 3, and then the point would be 0, 1. You had to change the x and y values. Now, when you're talking about lines, the mother function of a line is technically y equals x, okay? And we're going to kind of talk about a combination today of quadratics, relating it to like the slope intercept, which we'll call ready to graph, and this point slope, because it's kind of a lot of relationships to this too. And I think you're going to see why we need different forms of quadratics as well as different forms of lines. So what happens to y equals mx plus b if you change b? What happens to if you have y equals, let's say m is 2, 2x plus 4 versus y equals 2x minus 7? What does the b do to your graph? Well, what the b does to the graph is it moves your graph, translates it up or down. If the y-intercept would switch from 4 and the slope is 2, which is kind of a steeper line, that would be the plus 4, but if it was -7, it would be down here, but the same steepness. So this point would be moved from here to here. What does the m do? M measures the steepness. M is that rate of change, the steepness of the graph, and it affects the tilt. So like if it was 2x, we said it kind of looked like 2x plus 4 kind of looked like this, but if it was -1/2 x plus 4, then it would be flatter and a different tilt. Okay, so that's that rate of change. It affects the tilt or the slope. So we're going to look at the vertex form of a quadratic, which is this guy right here. And we're going to know what all of these parts do, the a, the h, and the k, just like we know what the b and the m does for mx plus b. And we're going to hopefully get pretty comfortable with that equation by the end of the lesson. Okay, so what is a transformation? These are geometry words, okay? The mother function of a quadratic is y equals x squared. So everything we do when we compare all of our graphs to what they originally are, we're going to compare it to the mother function, which if you remember has a point 0, 0, 1, 1, because 1 squared is 1, -1 squared is 1, and then 2, 4. Those are kind of the big points, 3, 9, 4, 16, you know. So when we do any comparison, we're going to compare it to this guy, which is the orange graph right here. Okay? So we're going to use these words from geometry, translation, which if you remember the not so smart word is slide. So if the orange graph is the original OG, then this one is translated to the left. Okay, these two are not translated at all. These are the stretch or the shrink was affected. And then this one is obviously reflected as well. So these are the words we're going to be using for quadratics. Okay, so let's remember what we know. Standard form. This stuff we already know, ax squared plus bx plus c. Okay, it's not still good for graphing. It's good for typing in our graphing calculator, and it's good for the y-intercept. It's really good for finding the y-intercept, and it's nice clean. It's a clean function. That's why we like typing it into our graphing calculator. Okay, factored form. What is factored form? That is there could be an a in front still. Let's say an x minus d, x minus e. And if you remember, these are good for the x-intercepts. Why is it good for the x-intercepts? Because you can plug 0 in for y, and then we know that one of those two guys would have to be 0 if y was 0. And it's good for solving if it's factored form, and the points would be d0, e0 for our x-intercepts. Here, the y-intercept would just be that constant, because when you plug in 0 for x, you just get c left over. Okay, and then the one we're going to talk about today, and you'll need to know this, is x minus h squared plus k. And this is called vertex form. It is definitely great for graphing. Okay, it is great for graphing. And the other nice thing is standard form and vertex form, all functions can be written this way. All quadratics, I should say. But remember, not all quadratics can be factored. And that process from going to standard to vertex is called completing the square. Okay, so basically what's going to happen today is, remember you had that ax plus by is c, and we would get y by itself. So that would be ready to graph, and then it would be like mx plus b. That's kind of what we're going to be doing today. You're going to have the standard form graph. We're going to complete the square so that it looks like this vertex form, and then we're going to know some stuff about the graph based on the way it looks. So what does this k on the last part, I'll just write the equation down again. The equation is a x minus h squared plus k. We're going to look at one piece at a time. So what does the k do? Okay, so basically we're going to try, what is x squared plus k? If you take away everything else and we're just dealing with the mother function here, adding k, what does it do to the graph? So there's a little thing I'd like you to click in. You can kind of explore with it a little bit, assuming I did it correctly. Okay, and there's a slider here. And so right now, x squared, we want the k to be 0, and that would be the mother function. So what happens if k is 1? What if it's x squared plus 1? So that the equation is x squared plus 1. What's it do? It kind of looks smaller, but it's not smaller. It's just you see less of the graph. All you're doing is moving it up. The parabola is the exact same. It is congruent all the time. It's just being moved up or down. And if k is negative, it's being moved down. And if k is positive, it's being moved up. So what does k do? Well, the mother function is x squared, and what k does, if it's greater than 0, it goes up, and if k is negative or less than 0, it goes down. So what I would write down, ax squared plus k, I would say that the k moves graph up or down. If it's a positive k, it goes up. And if it's a negative k, it goes down. And how far does it go down? Just the k units. So whatever k is how much up or down it moves. And that should make sense. If you think about a graphing our mother function that we talked about, if I was going to look at a table here, I put 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. If I take y equals x squared, and then I add 1 to it, when you have your xy, and I had negative 2, negative 1, 0, 1, and 2, when I take 0 squared and I add 1 to it, I'm actually adding 1 to the y values. So I'm adding 1 to all those y values. And if you add to the y, that is a vertical translation. It is a vertical shift, and it's going up 1 in this case because I'm adding to the y's. Okay, so what happens with those parentheses? So this is the equation again. A x minus h squared plus k. Because notice this has a minus sign in the parentheses. Okay, so the parenthesis is what we're looking at here. So just the a x minus h squared. And I just put 1 in for our example here. So we're all going to compare it to the mother function. This one's going to be a little bit different. You might have an idea already what you think is going to happen, but let's see if we can figure it out. Okay, here's the y equals x minus 0 squared. So this is the y equals x squared. What happens if you go to 1? X minus 1 squared. Well, looks like it went to the right 1. Looks like here I went to the right 4. So right is, and these are negative because it would be minus negative 6, which would be a plus 6 if it's a minus a negative 6. This might remind you a little bit about the point slope form of a graph because that's very much what this is like. And so what you have, x minus h squared, is this guy moves left or right. And what I like to tell myself is that the parentheses, it makes it counterintuitive. It makes it opposite of what you think. Because if it's an x minus 2 squared, I see a minus, and I might think to the left, but what I'm going is to the right 2. If it's x plus 3 squared, I'm going to go to the left 3. So you basically change the sign for the direction that you're going to go. And here's how they wrote it out for us. It is going to be a translation, a horizontal translation this time. And if h is greater than 0, it goes to the right. And if h is less than the 0, it goes to the left. But you have to remember that the sign has changed. So again, you might want to write it down however it makes sense to you, x minus h squared. It goes left or right h. If it's a minus an h or a plus an h, a minus h goes to the right h. And if it's a plus an h in the parentheses, then it goes to the left h. Okay, so in the parentheses, it's opposite of what you think, which I said is kind of similar to the x minus x1. Remember, you had to change the sign of the, it was y minus y1 equals mx minus x1 whenever you're talking about graphs. It's kind of similar to that. Okay, so let's put it all together. If you put it all together, then the vertex is going to be this, hk, because where the mother function is, which started at 0, 0, I'm going to go to the right h, and then I'm going to go up k, and that will be where my new 0, 0 is, or my new vertex. So hk is the vertex. Okay, this A we're going to talk about in a second. That's called the stretch factor, and we'll look at that in a minute. But right now, you need to know that HK is the vertex, and we can do both moves at once. Okay, so let's practice. Where will the vertex be? Okay, so I'm going to have my 0, 0. That's where the original mother function is. It looks like this. This guy, the plus 1, is going to move my graph up 1. What does the minus 2 do in the parentheses? It's kind of opposite of what you think. A minus sometimes what makes you want to think go to the left, but I'm going to go to the right 2. So I'm going to go to the right 2 and up 1, and that is where my new vertex is going to be. From there, we need to make the points the same that they would be from 0, 0. So our original OG function, the mother function, it always went from the 0, 0, if this was my 0, 0, it went over 1, up 1, left 1, up 1, because of symmetry. So from here, I'm going to go over 1, up 1 from my vertex. And then from my vertex, I'm going to go over 2, up 4. Because of 0.24. So from my vertex, go over 2. From my vertex, go up 4. And that was where my next point would be. Okay, so how do you get those other points? Here's what you do. From your vertex, you go over 1, up 1. You go over 2, up 4. If I wanted another point, I could go over 3, up 9, over 4, up 16, but nobody wants to graph that many points. Now, that's not the only way you could do it. I believe Mrs. Kazir taught some of you from the vertex, you can go over 1, up 1, over 1, up 3, over 1, up 5, and you can do that as well. You can do the 1, 3, 5 thing. Both of those work. Okay, so how do we graph this one? Well, where will the vertex be? The vertex will be, change the sign here. So I'm going to go to the right 3, and I'm going to go up 1. So from my original 0, 0, I'm going to go to the right 3 and up 1. And from there, I'm going to do my new points. Over 1, up 1. Over 2, up 4. It's really sloppy without the graph paper. Your other option, you could say over 1, up 1, over 1, up 3. Also perfectly fine. Okay. So what about the A? What else does that A do? Well, the A is what we call the stretch factor, kind of like a slope. So if, as 0.3 here, if A is 1, that's what the original function would be. If it is 1, where are you at? There it is. There's the original, right? If it's 2, it makes it thinner because the rate of change is greater, so it makes it steeper. Here it's 3. If it is less than 1, it gets wider because the rate of change is slower. Okay, so how do we relate that to our graphing? Well, let's sum it up first. If A is bigger than 1, it's a vertical stretch. If it's negative, obviously it flips and stretches. And if it's between -1 or those fractions less than 1, then it's going to get wider. Okay, do you need to memorize this? No, I think you'll know. What I like to tell kids to do is always go to that vertex first, from vertex. And you know how I said you go over 1, up 1? Really, it's over 1, up A, over 2, up 4 times A, over 3, up 9 times A, over 4, up 16 times A. Okay, that's how I like to think of it. Now, again, Mrs. Kazir, also good, so it goes over 1. It will also be up A, and then you can go over 1 again, and you could go up 3 times A, up 5 times A. You could do that way as well. But I like to see my original function, 1, 2, 3, 4, 1, 4, 9, 16, in my rules, because then it looks like the table where I started. Okay, so let's see what this looks like if I practice. Where are these points going to be? Okay, so I have my 0, 0. It's not moved left or right at all. So another way I can write that is y equals 1/4 x squared. So A is 1/4, which means it's going to get wider. So from here, I'm going to go over 1, up A, over 2, up 4A, over 3, up 9A, over 4, up 16A. And my A is 1/4. So I'm going to go over 1, up 1/4, which is not very high. Over 2, up 4 times 1/4, which means over 2, up 4 times 1/4 is 1. Over 3, up 9 times 1/4, which is not very helpful. But this next one is over 4, up 16 times 1/4, which means over 4, up 4. And that is enough points for me to get a good idea of how wide my parabola is. Whoop, that wasn't so good, but pretend it was. Okay, how about the 4x squared? So over 1, up 4, over 2, I shouldn't write it that way. I'm jumping the gun. 1a, 2, 4a, 3, 9a. So if it's a is 4 here, over 1 up 4, over 2 up 4 times 4, which is 16, over 3 up 9 times 4, which is 36, and we're not going to graph all those. It's going to be too steep. So I'm at 0, 0, 1, 4, 2, 16, and it's pretty steep here. Whoop, real skinny looking parabola. What about the negative 1/2? A is negative 1/2. So 1a, 2, 4a, 3, 9a. What do we have? Over 1, down a half. Over 2, 4 times negative 1/2 is down 2. Over 3, 9 times negative 1/2 is negative 4.5, and you can graph that as well. So 0, 0, over 1, down a half, over 2, down 2, always from the vertex, and over 3, down 4.5, out here, and there you go. How about the negative 16? Definitely don't want to do that. Over 1, down 16, over 2, down 4 times negative 16. That's going to get really steep really fast. Okay, so let's put it all together. Here we go. What is my vertex? I'm going to go change the sign. I'm going to go right 7. I'm going to go up 9, and that is my vertex. So do that first. Right 7, up 9, and that's my vertex. Now from there, I'm going to do the 1a, 2, 4a. So a is 5. So I'm going to go over 1, up 5, over 2, up 20 from my vertex. So over 1, up 5. Symmetry is beautiful. And then the other one's going to be even thinner than that. I don't have room to do it. Okay. So that's how you graph it. It's called speed graphing. Vertex form is so easy to graph. 7, 9, then your stretch factor. Okay, so what do I do here? Garbage. It's not the way I want it. The only thing I know from looking at this graph is that the y-intercept is 0, 5, which is a nice thing to know because I can check it. 0, negative 3, 0, 5, 0, 7. That's all I know from looking at these graphs because these are all in the wrong form. But we can change it by completing the square. So let's go ahead and practice that. If I complete the square, I need to know which square is closest to this guy. And remember, I have the x squared box, negative 4x's, so each side gets 2, and that one is the closest square. So it's an x minus 2 squared. If it's an x minus 2 squared, then there's 4 in the corner, but I have 5, so I need to add 1 more. So this guy is the exact same thing as x minus 2 squared plus 1. And if you don't believe me, I can actually prove it by multiplying up top. X minus 2 times x minus 2 plus 1. Double distribute here. X squared minus 4x plus 4 plus 1 is what I started with. But because it's in vertex form now, I can tell you what the vertex is. I'm going to go to the right 2 and up 1. So my vertex is the right 2, up 1, and I can put a point there. Now I can do my stretch factor. Well, my stretch is 1, a is 1. So from here, I'm just going to go over 1, up a, or over 1, up 1, over 2, up 4a, or 4, over 2, up 4, 1, 2, 3, 4 would be about here. And guess what? I can even check that my y-intercept is right, because there it is, right at 5. So what about this guy? What is it closest to? Well, he's closest to an x plus 4 squared. If there was 8, there would be 4 on each side. If you need to draw it, please do. That would put 16 in the corner, but I don't have 16. I have negative 3. So I'm going to have to subtract 16 and subtract 3 more. So I'm going to subtract 19. Okay, well, I don't want to graph this, but the vertex will be -4. Change that sign. Keep this sign, -19. The stretch factor is 1. Okay, so what do you do in cases like this? Well, these aren't as fun to complete the squares, but we can, and you really should. Your calculator can help you, and if you really struggle with this, I can show you a trick with that. But I want to show you how to do it by hand first. So this time there are 4x squareds, and I have -8x's. So each box gets how many? Well, -8x, I had to divide them up evenly. Divide it by 4. Each box gets -2x's. And each side will get -1. So each side is going to get -1x. So this is closest to 4 boxes of size x minus 1 square. What would be in the corner? Well, there'd be a 1 in the corner here and in all of these guys. So this picture has a total of 4 in the corner. But I need 1 more, so I'm going to add 1 more to get 5, and then that is my graph. How can I graph this now? Well, where's the vertex? I'm going to go to the right one and up 1 because I changed the sign of the parentheses and keep this sign. Stretch factor is 4, so I'm going to go over 1, up A, over 2, up 4A. So over 1, up 4, over 2, up 4 times 4, or 16. So over 1, up 4. There's that y-intercept right where I knew it would be. And then another one would be really steep up here. And there you go. Okay, let's try this last one here. This time there's 3 boxes. I have 12 x's for everybody. So each box gets 12 divided by 3, which would be 4x, and each side will get 2 x's. So this is closest to 3 boxes of size x plus 2 squared. And if that's the case, there'll be 4 here, and 4 here, which is 12. I don't have 12 though, I have 7, so I'm going to have to take away 5. And this is vertex form, and this is standard form. So what is my vertex? Well, there's a 2 in the parentheses, so I need to go to the left 2, which is a -2, down 5. So that is my vertex, -2, -5. And now I'm going to do my stretch factor, which is 3. So I'm going to go over 1, up A, or over 1, up 3, 2, 4A. So over 2, up 4 times 3 is 12. Over 1, up 3. And then I'll use symmetry. Now over 2, up 4 times 3, up 12. So I'm going to go up 5 and up 7 more. And guess what? There's that y-intercept of 7 where I thought it would be. There it is. Kind of sloppy, but you get the idea. Okay, is that it? I think we're done. All right. So what if it's in factored form? I didn't show you any of those. If it was in factored form, what you would need to do is you would need to, let's say this is, I don't want to do that one, x plus 4, x minus 2. You would need to put it in standard form first, x squared minus 2x plus 4x, that's plus 2x minus 8, and then complete the square just like what we just did. So you have to go through standard form to get to vertex form. Okay, but overall that's it, and hopefully you'll get some nice practice on the worksheet.